So first talk we have, starting, we've got Sylvain Lacroix from Hamburg, who's going to tell us about integral sigma models.
Okay, thank you. So good afternoon, everyone. So it's a pleasure for me to participate in this North British Mathematical Physics seminar. So first, I would like to thank the organizer for giving me this opportunity to talk today. And so I would like to present some recent development about integrable sigma models based on two collaborations, one with Kleber Otunov and Christian Bassi, and the other one with François Delduc, Konstantinos Vetsos, and Konstantinos Siampos. So today I will be interested in integrable field theories, which are certain field theories which possess an infinite number of symmetries, which are quite constraining on the model, which then allows the development of exact methods to compute physical observables in these systems. And I will also be interested in sigma models, which are particular two-dimensional field theories whose field takes value on a certain Riemannian target space and which have application in various domains of physics, such as string theory, condensed matter, high energy physics, and conformal field theories and others. And more precisely, I will be interested in the intersection of these two classes, which is that for a good choice of the target space on which a sigma model is defined, the model can then be integrable. And among all possible sigma models, the integrable one are quite rare, but still we have a growing list of examples over the year. And the simplest example would be what is called the principal Carroll model, which is the case where their target space is Lie group G. And there are also symmetric space sigma model, where the target space is a certain quotient of a Lie group G by a specific subgroup H, or also to cite another important example, which is the superstring on ADS5 cross S5, which plays a key role in the ADS CFT correspondence, and actually integrability was an important tool for the study of this correspondence. And recently, there was also a regain of interest for the study of these integrable sigma models because of the discovery of some continuous deformations of these models which preserve their integrability. And these deformations then provide us with a whole family of integrable field theories. And a natural question at this point is then whether there exists a unifying common structure behind the integrability of all these models. And the answer is yes, they are all what are called models with twist functions. So I will come back on this notion of twist function later in the talk. And more recently, also, all these have been reinterpreted as what are called affine Godin models, which are related to representation theory of affine Kac-Moody algebras. And so one can wonder what are applications of having this reinterpretation of all these as affine Godin models. And well, the first motivation was actually to gain some insight about some of the quantum properties of these models, but there are also the application, in particular, for instance, the construction of new integrable sigma models. And a typical example of that is some integrable model on n copies of a Lie group G, which are then given by n copies of the principal Carroll model, which are coupled together in a way that ensures that the theory is integral. And so the subject of this talk would be two recent development in this direction. The first one being the study of the one loop renormalization of the integrable model and n copy of G. And the second one is yet another class of new examples of integrable model, which are defined on certain cosets of n copies of a group G by a certain diagonal subgroup. So the plan of my talk is a bit the following. So first I will explain what in general are integrable field theories with twist function. Then I will describe these coupled principal Carroll models and discuss their renormalization. And finally, I will discuss these new integrable coset models before concluding. So let me start with integrable field theories with twist function. So we'll be concerned with two-dimensional classical field theories, which depend on the time coordinate t and a space coordinate x. And we can take x either on the real line or on the cycle, and we just take the appropriate boundary conditions. And we'll look at it in the Hamiltonian formalism. So we will have a Poisson bracket on the phase space of fields, and then the time evolution will be given by the Poisson bracket of the Hamiltonian. And we'll say that this model is integrable if it possesses an infinite number of conserved charges in involution. So conserved meaning that they Poisson commute with the Hamiltonian, and involution meaning that they Poisson commute pairwise. A natural question then is, how can one build integrable field theories? How can one build these charges in involution? And this is often done by what is called the lax formalism. So we say that the model possesses a lax connection if it has a pair of matrices L and M, which are valued in a certain Lie algebra G, which depend on the fields of the model, so which depend then on the space-time coordinate T and X, and also on an auxiliary complex parameter Z called the spectral parameter, such that the equation of motions of the system can be recast as the following zero curvature equation on L and M, where here this bracket is the commutator in the Lie algebra. And if we have this, then we can look at the monodromy matrix of L, which is defined so as a path-ordered exponential of L. So here I take it from 0 to 2 pi on a cycle, but we can also consider it from -infinity to +infinity if we were on the real line. And the result is then that if the dynamic of L is given by the zero curvature equation, then the traces of powers of this monodromy matrix are conserved quantities, so they do not depend on time. And because we also ask that this zero curvature equation is true for every value of this auxiliary parameter Z, then we can vary this Z, or we can expand in Z, for example, and this then gives us an infinite number of conserved quantities. And so that's a good first step towards proving the integrability of the model. But to really get to the integrability, one would need to have that these charges are in involution, so we need to study the Poisson bracket. And because they're defined from the monodromy, which itself is defined from L, this leads us to study the Poisson bracket between the components of L, and this then will lead us to what is called a Mayer bracket. So I will fix a basis of the Lie algebra G, and then which allows us to decompose the lax matrix along this basis. So these LA now are the components of this lax matrix. And because now we'll look at Poisson bracket, I will remove time. I will work at a fixed value of time, and now time evolution is just given by the Poisson bracket with the Hamilton. And then I will use tensorial notation, which is that if I have, for example, a matrix A in the Lie algebra, I will call A1 a tensor identity, and similarly for B2 here. And using that, we can encode all the Poisson bracket between different components of the lax matrix at different values of the spectral parameters and different values of the space coordinate X and Y into the following objects by contracting them with the basis IA tensor IB. And this is then an element in G tensor G, which encode all the Poisson brackets. And now the question is there a condition on this bracket which would ensure that the charges extracted from the monodromy are all in involution, which would then prove the integrability of the system. And indeed, there is such a condition, which is what is called the Mayer non-neutral local bracket, which takes the following form here. So in this expression, delta is the Dirac distribution. So we're looking at Poisson bracket of fields at space coordinate X and Y. So indeed, we expect some Dirac distribution. And these are called in the ultra-local term. And we have also some derivative of this Dirac distribution, which are what are called the non-neutral local term. And this bracket then take a very specific form in terms of a certain element of G tensor G, which depend on the spectral parameters Z and W, and which we call the R matrix of the system. And this is then what characterizes the integrable structure of the system at the Hamiltonian level. And so one can wonder, do we have any constraints on this R matrix? Can we take any possible R? And for that, we will need to look at the properties of the Poisson bracket. So a Poisson bracket should always be skew symmetric, but actually the way this is defined, one shows that it's automatically skew symmetric. And a Poisson bracket should also satisfy the Jacobi identity. And this actually puts some constraints on which matrix R we can take. And a way to satisfy this constraint is to ask that R satisfy the so-called classical Yang-Baxter equation, which is given by the following expression, and which is a purely algebraic condition on R, which involve commutators in free tensor spaces. And a typical example of a solution of this equation is given by the following construction. So we take G to be semi-simple, in which case the killing form on G is non-degenerate. So if we have a basis of the Lie algebra, we can consider its dual basis, and we can construct what is called a Casimir of G, which is the basis tensored with its dual basis. And this is then an element of G tensor G. And then the result is that because of the properties of the killing form, in particular the fact that the killing form is invariant in the commutator, one shows that the Casimir divided by W minus Z is a solution of this classical Yang-Baxter equation. And now I would like to make a quite simple but important observation for this talk, which is the following. So if we start with a fixed solution R0 of this classical Yang-Baxter equation, so typically this Casimir divided by W minus Z, and we multiply it by function of the second spectral parameter W, and this function I will call it phi inverse, then we get another solution, because we see that in the equation, the second spectral parameters are always Z2 and Z3. So the function will just factorize out and we'll get another solution. So starting with a fixed solution, we get an infinite family of solution labeled by a certain rational function phi of the spectral parameter. And this is exactly what I called in introduction, the twist function. So this twist function, it's a way of characterizing then the integrable structure of the model at the Hamiltonian level. And as I said also, recently models with twist functions, so with R matrix take this form for certain R0, they have been reinterpreted in terms of the representation theory of Cox-Moody algebra, what are called affine Godin models. And these affine Godin models, they played, so in this paper by Benoit Vicedo, and they played an important role in some of the construction that we'll talk about today, but I will not enter into the details of this construction, and actually we'll just talk about the end results. And so now, just before going to explicit example of all this formalism, I would just make an observation that so far we use zero curvature equation using the time and space coordinate T and X. But because we'll be looking at relativistic model, it will actually be more useful to use light cone coordinate T plus minus X over 2 and the corresponding derivative. And in this case, we can look for the Lax connection and the zero curvature equation in the following light cone form, which will be more useful for us. And now that I presented this general formalism, I would then like to present applications of this, in particular describing the coupled principal chiral models that I mentioned in the renormalisation. And for that, I would like to start with just one copy of this principal chiral model. So this PCM, principal chiral model, as I said, is a sigma model on a Lie group G. So here, this Lie group, for simplicity, we can think of it as just being a matricial Lie group. So for example, SUN, SON, or SLN. And then the model depends on one field, which is valued in the group G, and which depend on the 2D Minkowski coordinate, T and X. So it can be seen as a matrix whose entries are fields. Then we can define the Morikaten currents, G inverse dG, and because G is in the group, these currents are naturally valued in the Lie algebra. And we then define the action of the PCM by integrating over space-time the trace of J plus and J minus, so quadratic in current. And this then defines a functional of the field G. And because we have a functional, we can look at its variation and then the corresponding equation of motion of the system. And here we simply find that these equations of motion are a conservation equation for these currents, J plus and J minus. Moreover, these currents, they satisfy another equation, which is called the Morikaten identity, which is the following here, which is true just by definition of what is J plus and J minus. So this is true off shell, even without the equation of motion. And by combining these two equations, one shows that the model possesses a Lax connection, which is given by the following expression here in light cone coordinates, in which dependent on the spectral parameter Z. So from these two equations, one shows that this connection satisfies a zero curvature equation for all values of Z. And this, as I mentioned before, shows that it possesses an infinite number of conserved quantities. And then to completely prove the integrability of the model, we need to prove that these charges are involution. And for that, we need to study the Poisson bracket of the Lax matrix, so this spatial component of this Lax connection. And for that, I will skip all the details, but one can do the Hamiltonian analysis, the canonical brackets, and so on. And in the end, one finds that the Poisson bracket of the Lax matrix takes the form of a Maillet non-neutral local bracket, as I presented before, where the R matrix is given by the Casimir divided by W minus Z times a twist function of the second spectral parameter W. And for the case of the PCM, this twist function is given by 1 minus Z squared over Z squared. In particular, it has a double pole at Z equals 0. As you see, this will be important. So there exists a modification of this construction, which is to add to the model what is called the Wess-Zumino term. So I won't enter into the details of how this term is constructed. It is, in some sense, a topological 3D term. But the idea is just that we can add it to the action with some prefactor K. And this actually has some application to CFTs because when k equal plus or minus 1, we then get a conformal model, which is the Vezdumino-Novikov-Witten model. And then for all values of k, and the addition of this term will change the equation of motion of the system, which still is a conservation equation, but with the coefficients here modified by k. And what's important is that this model is still integrable, so it still possesses a lax connection, which is just a modification of the one we had before by k. And it still satisfies a Maya bracket with twist function. And the effect of adding the Vezdumino term on a twist function is to shift the double pole at z equals 0 to a double pole at z equal k. And now that I presented this, I can present this coupled principal curl model that I mentioned, so which were constructed in this article about 2 years ago now. And the idea is to just observe that the principal curl model, with or without Vezdumino term, correspond to a twist function with one double pole. So it's natural to wonder if one can actually construct an integrable model with a twist function which would possess n double pole. So for that, we will parameterize this twist function in the following way. So as a factorized form, phi plus, phi minus, where these phi plus and phi minus have poles at the points zr. So in the end, these will be double poles of the twist function. And they're also parameterized by the zeros, which we call zeta plus r and zeta minus r, which are separated into two sets, zeta plus and zeta minus for some reason. And this twist function is then parameterized by free n parameters, the z's and the zetas. And then the question is, can we construct an integrable model which have this twist function? This is actually a non-trivial question, and this is where the formalism of affine Godin model are useful. And using this formalism, one can construct then such a model which will then be automatically integrable, and it is constructed at the Hamiltonian law. So I will skip all this construction, and then what you can do is going to the Lagrangian formulation by an inverse Legendre transform, we can get an action for this model, and I will just describe then the final action that we get. So it depends on n fields, G1 up to Gn, which are all valued in the group, and which have all their own currents. And then each of the field will possess its own Vezdumino term with some coefficient Kr. And then there will be some PCM-like term, some quadratic interaction between the currents, and controlled by a coefficient rho rs, and with non-trivial interactions between different copies. So this is a coupled model. And of course, for generic values of rho and k, this model is not integrable, but because we're constructing a model from affine Godin model, which are automatically integrable, then this one will be, and it will correspond to a very specific choice of the coefficients rho and k, which are given to be complete by the following expression in terms of certain residues of well-chosen function in terms of the twist function and the phi plus and phi minus. So in the end, these are expression in terms of the parameters z and zetas defining the twist function. And so now what I would like to talk about is the geometry of this model. And for that, it is useful to introduce local coordinates on the manifold Gn on which it is defined. So now instead of having n fields which are valued in the group, we can describe the model in terms of n times the dimension of the group, scalar fields y mu, which are now fields just valued in the real numbers. And using these coordinates, we can always rewrite the action, well, at least locally. There might be some global subtlety, but at least locally, we can always rewrite the action in the standard sigma model form, which is quadratic terms in the derivative of the coordinates contracted with some tensor on the manifold. And this tensor, it has a symmetric part, which is simply the metric on the manifold. So here I call it G twiddle for a reason to become a bit clearer after. And it also has a skew symmetric part, B, which we call the B field. And in this particular case where the model is on n copy of G, then the geometry will always decompose. So for example, the metric will always decompose in a part which describes the internal geometry of one copy of the group, factorized with a part which describes the interaction between different copies. And for instance, for the metric, this part which describes interaction between the different copies is just the symmetrization of the coefficients rho rs appearing in the action. And similarly, for the B field, we'll have the skew symmetrization of this coefficient. And by a slight abuse of notation, I will still call G and B the metric and B field of the model. And now I would like to talk about renormalization. of sigma models. And so because there exists general results about renormalization of any sigma models of this form. So one can look at the one loop Feynman diagrams coming from this model. One finds some UV divergences that one need to then renormalize the theory and add some contour terms. And this will then lead to the fact that there is a renormalization group flow for the model. So here I will use the parameter tau to describe it, which is related to the log of the mass scale of the RG flow. And then the result is that the metric plus B field of the model flows under the RG, and its flow is given by what is called a torsionful Ricci tensor of the geometry, which is a purely geometric model. So in the case where we have no B field, just a metric, then in this case we have not the torsionful tensor, but just the standard Ricci tensor, which is the one we have, for instance, in general relativity, and which describes the curvature of the Levi-Civita connection, which is given by the Christoffel symbol, so with derivative of the metric, and here with the inverse metric. And in the case where we have a B field, when we need to add torsion to this system, which is that now we're looking at the curvature of a generalized connection, which is the Christoffel symbol to which we add something called the torsion of the B field. And these then are general results for any sigma models. And now if we apply it to these coupled principal Corot models that are presented before, and this is then the results of this recent work with François Delduc, Konstantinos Vetsos, and Konstantinos Siampos, then these general results translate to a flow of the parameters in the geometry describing the interaction between the copies. So these parameters rho RS in the action. What we see is that the flow of these rho RS is given by the part of the Ricci tensor that describe the interaction between the copies. So once again, we kind of forget about the part in the internal geometry. And we also find that the coefficients of the Vesemino term, Kr, they actually do not flow under the RG. And this is because the Vesemino term are kind of topological 3D terms, so they are in some sense topologically protected under the RG flow. And this result is actually true for all possible rho RS and K. And now the natural question is, if we take the integrable model, so which corresponded to specific choices of rho and K, is this model also one loop renormalizable? Or in other words, does this specific choice of rho and K, is it preserved by this one loop RG? And to answer this question, we need to know a bit about the geometry of the model. And for that, we will need to introduce some functions related to the twist function. So if one look at the inverse of the twist function of the model, then one finds that it has poles at the zeros of phi, so zeta plus and zeta minus. And one easily shows that its partial fraction decomposition is given by this. And then we can introduce a certain function f, which is defined in almost the same way, just with a minus sign here in the definition, and where a is just an arbitrary constant. And then this function f turns out to be quite useful to describe the geometry of this integrable model. So for instance, if we consider the metric of the model and we invert it, we raise the indices, then one finds that actually this inverse matrix is given by the following expression in terms of this function f and the poles zr of the twist function. And one also finds that the B field can also be expressed in terms of f, and this leads, for example, to some identities relating the B field and the metric, such as, for example, this one. And we then get various other identities on the geometry of the model and also on the Ricci tensor of this model. And then plugging this inside of the RG flow. So I skip all the details. If you want detail, they're in the paper. In the end, what we find is that this integrable coupled model is indeed one loop renormalizable. And we find that the defining parameters of the model, which are the poles and zeros of the twist function, they then run under this RG flow. And for instance, the poles, their RG flow is given by the following expression. So CG times FZR, where F is the function we just introduced, and CG is the value of the quadratic Casimir of the group in the adjoint representation, which then just is the global factor that keeps tracks of which group we've chosen originally. And one would find that also the zeros and zetas run under the RG. So describing their flow would require introducing a few more notations. So I will actually not do it, because in some sense we will do now something simpler. Because recall that all these parameters, they're all encoded into one unique object, which is the twist function. So it's quite tempting to try to rewrite the RG flow as uniquely a simple equation on the twist function itself. And not only this turns out to be possible, but it in the end gives a rather simple and compact way of writing the full RG flow of the model. So which is given by the following expression. So the RG flow of the twist function is given by the following expression here in terms of the function f that we introduced before in some derivative with respect to the spectral parameter. And now that we also get this RG flow written in terms of the twist function, it is natural to wonder if it actually can be more universal, if it actually applies to any integrable sigma models with twist function. And so this is what we conjecture, and we check this on some examples. So in particular, we check this for what are called the Yang-Baxter and lambda deformations of one copy of the PCM, so which are certain integrable deformations, for which the RG flow was already known before. And what we checked is that what is known about the RG flow can be recast into the following expression in terms of the twist function. And we also checked it for what is called the double lambda model. So that then ends what I wanted to say about this renormalization of coupled models. Now I would like to finish on presenting some new recent development with other examples of integrable sigma models, which are this time coset models. So for that, I will start by describing symmetric spaces. So we start with a group G, which possesses an involutive automorphism sigma, so which preserves the multiplication on the group and which squares to the identity. So that's the involution property. And we can then look at the fixed points of this automorphism, and which always form a subgroup G0 of G. We can then look at the quotient of G by G0, and this is exactly what we define as a symmetric space coset. And a typical example of this is the spheres in n dimension, which is given by the quotient of SON plus 1 by SON. Also, another example are the ADS spaces, which are just a non-compact version of this coset construction. And at the Lie algebra level, so sigma will induce an automorphism of the Lie algebra G, which have two eigenspaces with eigenvalue +1 and -1. And these form what is called a Z2 gradation of the Lie algebra. So the algebra is G0 plus G1, where the commutator of G0 with G0 closes in G0. So G0 is a Lie algebra, Lie subalgebra, which correspond to this subgroup. Then G0 with G1 closes in G1. And finally, G1 with G1 closes back in G0. So what we call the Z2 gradation. And then for every element of the Lie algebra, we can decompose it as a part in the grading 0 plus a part in the grading 1. And with that, we can define the symmetric space sigma model in the following way. So it depends, again, on the field valued in the group. And the action is given by almost the same action as the principal Carroll model, but now we just keep only the grading 1 parts of the currents. And the effect of taking this grading 1 part is that this introduces a gauge symmetry on the model. So if we take the group valued field and we multiply it on the right by a function h, which is any function valued in a subgroup G0, well, one shows that the grading of the Morikaten currents, they behave under the following way under this transformation. And in particular, the grading 1 just behaves covariantly. So it transforms just by conjugation by h. And because the trace is invariant in the conjugation, we get that this leaves the action of the model completely invariant. So this introduces a gauge symmetry by G0. And we then see that the model is then equivalent to a model on the coset G by G0, because we can gauge out all the degrees of freedom in G0. And this is how we get a model on the symmetric space coset as a gauge model on G with a gauge symmetry. And this model turns out to also be integrable. So it possesses a lax connection, and it satisfies a Mayer bracket with twist function. So this Mayer bracket, the R matrix, is given by the following expression. So it resembled the one we had before with Casimir divided by W minus Z. But now we have a second part where there is the automorphism sigma appearing, which then keeps tracks of what is the automorphism sigma and what is then the subgroup G0 by which we quotient. And this then form what is called the sigma twisted R matrix, which also satisfy the classical Yang-Baxter equation due to the fact that sigma is an automorphism. And then we get this R matrix times twist function of the second spectral parameter W. And for the case then of the symmetric space model, this twist function is given by the following expression. And we also keep track of sigma by the fact that the model satisfies what are called Z2 equivalence properties, which is that if we take L at minus Z, we get sigma of LZ. And also if we take phi at minus Z, we get minus phi Z. So the twist function is an odd function of the spectral part. And then models which have the following R matrix with a twist function and which satisfy these equivalence properties are also affine Godin models, which are called dihedral affine Godin models. And this dihedrality property is related to these equivalence properties by sigma. And just a remark here is that because of this property that phi is an odd function of the spectral parameter, we see that if we have a pole at the point Z, then there is also a pole at the point minus Z. So poles come by pairs now. So for instance, here we have poles at +1 and -1. And now what I would like to present is the construction of new integrable coset models, so which is based on this recent work with Gleb Aotunov and Christian Bassi. And the idea is to start with the observation that the symmetric space sigma model corresponds to a twist function with one pair of poles. So it's natural to wonder if we can do the same thing as what we did for the PCM before and construct a new model with twist function which would possess then n pair of double poles. And for that, we will write the twist function in the factorized form, phi plus phi minus as before. And the phi plus phi minus, they're then defined in terms of their poles and their zeros. And they're defined in a similar way at what we had before. The main difference between that now we have some squares, Z squares everywhere to keep track of the equivalence property of Z going to minus Z. And then the question is, can we construct a model with an integrable model with this corresponding twist function? And here, once again, we'll do it at the Hamiltonian level using the formalism of dihedral affine Godin models. And this then can be done for any n. And this gives a model which is integrable by construction and which depends then on 3n-2 parameters, which are the zeros and the poles in the twist function. So I will once again skip all the details about this Hamiltonian construction and we'll talk only about the action that we obtained by doing the inverse Laplacian transform. So technically, actually, we did it explicitly only for the case of n smaller than 3, but this actually led us to a conjecture for any value of n, and which is given by the following. So this action depends on n fields in the group. Each of these fields has its own Vesimilo term, and then we get some interaction quadratic in the currents. And the main difference with the PCM case that I presented before is that now we have a decomposition in the grading 0 and 1, keeping track of the automorphism sigma that we chose. And the coefficient k and rho, which ensures the integrability of the model, they're given by the following expressions, so which are still some residues of well-chosen function phi and phi plus phi minus, so which are quite close to the expressions we had before. But here in the expression of rho, we have some different expression which keep track of this equivalence z to minus z. And an important property of this action, in addition to the fact that it's integrable, is that it possesses a gauge symmetry. So if I take all the fields gr and multiply them all on the right by the same function h valued in the subgroup G0, one shows that this is a local gauge symmetry of the model. So we see that we have a gauge symmetry by the diagonal action of the group G0. So diagonal because it acts simultaneously on all the fields in all the copies. And what we see is then that the model is equivalent to a model on the coset of Gn by the diagonal subgroup G0. Right? And so these are the new examples, coset examples that I wanted to present. And then I would like to present some example application of that to the simplest example that one can find beyond symmetric space models, which is the case with two copies, and where the group is the simplest one we can think of, which is SU2. And then in this case, we'll divide by the subgroup U1 in the diagonal. For that, we can parameterize the fields, two fields, G1 and G2 in SU2 using Euler angles. And so using polar polymatrices sigma I. And in this parameterization, the fields then depend on 6 coordinates, which are 6 angles, phi1, theta1, psi, and phi2, theta2, psi2. And the gauge symmetry, which acts on the right simultaneously on these two elements, then acts just by translation of the angles psi and psi twiddle. And in particular, then we can gauge fix the model by setting psi twiddle to 0, and we then get a model on the remaining local coordinates phi 1, theta 1, phi 2, theta 2 psi, which are the coordinate describing this concept. And by a bit of work, we can put the action in the standard sigma model form, right, depending on a certain metric and a B field. And these metrics and B field, in general, they would depend on all the parameters in the twist function. So in this case, there are 4, 2 poles of the twist function, and then 2 zeros, theta plus and theta minus. And actually here we'll be interested into just a certain limit, specific limit of these parameters when one is scaled away. And in the end, this will give us an integrable model, which depends on only 3 parameters, lambda 1, lambda 2, and lambda. And then to describe this end result, so the metric given in the ds squared form in coordinates, so is given by the following expression in terms of the angle coordinates and the parameters lambda 1, lambda 2, and lambda. And these are exactly the metric of what are called T11 manifolds, which have been studied in the literature before, in particular related to supergravity and the ADS CFT correspondence. And in our case, we also have a B field, which we write in terms of differential forms, right? We're using a wedge. And this B field takes the following expression. And in particular, remark that the coefficient lambda squared in this B field is exactly the same coefficient as this part here of the metric. And the fact that this is the same coefficient is actually quite important for the integrability of the model. So if we would take another B field, or even just change the coefficient here in the metric, in the B field, we would break integrability. And this is consistent with what is known in the literature, in particular in some articles by Basu and Pondosayas, where they study the same model in the same metric, but now this no B field. And they study what are called wrap string solutions in these systems, and they find that these are chaotic, so it cannot be integrable. And so because of that, it was long time believed that models, integrable sigma models, on T11 cannot be integrable. And the result of this construction by affine Godin models is that they actually can be if we choose the B field very carefully with the good coefficient. And so then that ends up what I wanted to say. So just to finish by a conclusion and perspective. So about the renormalization part. So we got this conjecture for the one loop RG flow of all integrable sigma models with twist functions. So it would be nice to check this conjecture for other models. So for instance, deformations of the coupled model that I present, also for the coset models that I just mentioned. And of course, it would be interesting to find a general proof. And if we have such a general proof, to find an interpretation in terms of affine Godin models, or what is called 4D Chern-Simons theory, which is another alternative way of studying, unifying way of studying integrable sigma models, which was recently proposed by Costello and Yamazaki, and which was a bit later shown to be quite deeply related to affine Godin models. Other interesting question would concern also the higher loop renormalization on models. So there exist general results about higher loop renormalization of sigma models, also related to their geometry. And in general, this higher loop renormalization requires adding quantum corrections to the geometry of the model. And in particular for integrable sigma models and for a certain specific integrable deformation, it was this question of higher loop renormalization was studied recently in some paper here. And it would be interesting to see, to study the higher loop renormalization of the coupled model and see if in this case we also need quantum correction. And finally, it would be maybe interesting to study a bit more a certain relation that was put forward recently in this paper about the relation between the RG flow of integrable sigma models and the integrability of the models with local coupling. So where the coupling now depends on the space-time coordinate Tnx. And what it was shown is that this integrability is actually related to the RG flow of the theory. So it would be interesting to see if this still holds, for example, for the case of the coupled model. And finally, a few perspectives about the integrable coset models. So as I said, the form of the action that I presented was actually only a conjecture. It was only checked up to n equals 3. So it would be nice to check this conjecture for any n. And also it would be nice to study generalization of that to what are called ZT cosets. So which are the case where the automorphism sigma is not of order 2, but actually of a general order, finite order T. I don't know if is there a question? I hear some. No. Okay. And then for the ZT cosets, the integrable models are known for one copy of the group by some work of Charles Young. And actually in what I presented, we actually found a conjecture for the action for any number of copies. So it would be interesting to maybe study this in more details. And I think maybe the most promising here perspective would be to study integrable models now defined on cosets of supergroups instead of just only groups to add some fermionic degrees of freedom in the models. And this could be done, for example, by looking at affine Godin models based on superalgebras. And a natural question in this context is to study whether we can find then some new integrable superstrings. And the natural related question is whether we can embed the T11 integrable model I presented into a supergravity background. And this then ends what I wanted to present. So I thank you for your attention.
Great, thank you. So do we have any questions? I think if you want to just unmute yourself and speak up.
So can I ask a quick question?
Sure.
I have a couple. The first one is to do with this function f that you presented related.
Yes.
I don't know whether or not, but that sort of just from, it seemed, the definition of it seemed a little bit ad hoc. Sort of change this plus sign to a minus sign, change this one to a. Do you have some kind of idea if there's a kind of a prescriptive way or a sort of concrete way of saying f in terms of phi is this? Or?
Well, okay. I mean, here the main motivation for it is that it worked somehow. It was, I mean, we define f because it was what we found for this inverse metric. Then, as I said, I mean, I skipped the details on this, but the zeros of the twist function are naturally separated into two sets, which are this zeta plus and zeta minus, which are naturally associated to actually coefficients which are +1 and -1. And these are coefficients that actually enter the definition of the Hamiltonian of the model. So in general, actually, this function f is defined by the choice of the twist function and its inverse. And we have to actually put some information in it, which is related to the choice of the Hamiltonian, because we know that different Hamiltonians should give different RG flows. Okay. And actually, this choice of Hamiltonian is some coefficients epsilon I, which are either +1 or -1 in our case, and which then enters here this definition of f.
I see. Okay, so there is a kind of deeper, story behind that. And the constant a is.
The constant a actually just reflect the fact, something that I didn't say, that actually all the models here, it's invariant if we change all the poles and the zeros if we translate them by the same number. So, which means that actually, for example, if I look at the flow of ZR, I can shift it by a constant. It won't change the model. Actually, there is a freedom in translating everything, and this is then in f. And what we see also is that in this expression for the inverse metric, whatever a I put, it won't appear. It will always simplify.
And then I had another quick question. I don't know if that's okay, if I have another quick question. About these coupled models, so the ones you've been talking about, are their RG flow protected by symmetry at all, or is it, I can't?
So it's not completely obvious. So they possess n+1 global symmetry by G. So n of them that acts on the left Gn. And then there is also the diagonal one acting on the right Gn.
Okay, so probably not enough to.
And probably I think it's not enough to, I mean, in some sense, it will just tell us that, and even before taking only the integrable model, it will tell us that only the rows and k only the row should flow, basically, and we still preserve this form in terms of row. But then for this integrable case, there are additional symmetries, but they're quite non-local and quite hidden, so it's not clear how to use them to really constrain the RG flow, at least to my knowledge.
Okay, so thank you.